The motivation of this demonstration stemmed from the fact that we were interested in studying kinematics with the concept of kinetic energy to explain the reason behind the perceived phenomena. We believe that archery, using a toy bow and arrow, would be exemplary of our thoughts as, intuitively, the further the bowstring is pulled back, the faster the arrow is propelled. This later becomes evident through the greater initial velocity observed in the experiment. Alternatively, we can analyze the kinetic energy released using the following formula. It can be said that kinetic energy is proportional to the square of velocity. If speed is doubled, we would expect kinetic energy to quadruple, and so on. This experiment intended to model doubling the speed by varying the deformation of the bowstring to where we observed the initial velocity doubling. However, due to this task being difficult to replicate in action, we observed a greater difference in velocity, not necessarily double of the first trial. In terms of the experimental setup, our partner, Preeti, decided to do the demonstration of shooting a bow utilizing different pull strains. As a side note, this experiment was done completely COVID safe, where a group opted to have only one member do the experiment at home, as to reduce the spread of COVID. The experiment took place in her backyard. The first trial consisted of Preeti pulling the bowstring with minimal effort to demonstrate a smaller initial velocity. In the second trial, Preeti increased the pulling strain, or in technical terms, attempted a full draw to show a faster propelled arrow. If this is not clear, Preeti wore different colored shirts in the two videos to be able to easily differentiate between the two. Each trial was analyzed separately in the video analysis program, and a graph measuring x velocity versus time was generated for both situations. Both graphs exhibited constant velocity just after the release of the arrow. The average points of the release time was computed to represent the initial velocity of the arrow. This can be justified by the fact that no net forces are acting upon the arrow in the horizontal direction. Therefore, by virtue of Newton's first law, the arrow would continue its motion in the same propelled direction, moving at a constant speed. We can safely disregard the acceleration induced by the net force, i.e. weight, in the vertical direction due to it being minuscule. In another manner, one can manifest the law of conservation of energy in that the total energy involved in the process of shooting a bow remains constant over the entire duration. Energy, however, can transform from one type to another, or from one part to another, which is what we witnessed in this experiment. The bow stores the elastic potential energy as the arrow is drawn back. Once it is released, the potential energy of the stretched bow is converted into kinetic energy of the propelled arrow. In the first trial, where the pulling strain is minimal, the observed initial speed was 9.200 meters per second. Therefore, the observed kinetic energy was 0.302 joules. In the second trial, where the pulling strain was the highest, the observed initial speed of the arrow was 12.104 meters per second. The observed kinetic energy for this trial was calculated to be 0.523 joules. This trend shows that the more pulling strain is applied to the bowstring, the faster the arrow is propelled, and therefore the greater the kinetic energy.